Hey everybody, Miss Rector's here. We are going to go over Chapter 3, Section 2 that you have read now. So um, this is getting after Dalton. So let's go further into what was discovered in the atom afterwards. So um, after Dalton comes along, you have a lot of people studying new stuff in science, and one of the new things coming up is electricity. So let's talk about a couple of the people involved there. So Faraday was the first person to suggest that the structure of the atom was somehow related to electricity. He wasn't quite sure how it was, but he thought atoms must contain particles that have some electrical charge. And if you're not familiar with Faraday, this is an example of a Faraday flashlight. You may have seen these before. These are the kind of flashlights that you shake. So it's got this copper coil of wire here and this magnet. And as you pass the magnet back and forth, so you shake the flashlight, it sends an electrical current through the wire, which will charge a little battery here and charge your flashlight. So when you shake it back and forth, then you charge your battery and get electricity. So this is how power is produced at all power plants, like a Faraday generator. You have a big coil of wire and a magnet, and that's all you need to make an electric current. So what Faraday was saying is that, something must be happening in the atom when I pass this magnet back and forth. Some kind of charge must be moving in it to make this electric current. Another name you might already know when you think of electricity, Benjamin Franklin. So we all know about his, kite experiment and all that. He was basically discovering static electricity, that there was this static charge buildup of electricity that could be, discharged when it came around another charge. So he figured out there were two kinds of charges. He chose to call them positive and negative. And he found that like charges would repel each other while opposites would attract. He also concluded that lightning is a sudden discharge of electricity between the cloud and the ground. And it took about 100 years before somebody actually determines where these charges are coming from. So who determines that? Here we go. So now we're going to talk about Thomson's plum pudding model of the atom. So the person who comes up with this, the next big jump in atomic theory, is J.J. Thomson. So J.J. Thomson is working with something called cathode rays. And if you ever had like those televisions that have like the big back on them, like they're big, not the flat screens, but the big box TVs, those had cathode rays in them back in the day. So when cathode rays were discovered, people, all kinds of scientists were just really interested in them, doing all kinds of experiments. And J.J. Thomson was one of those. So he's working with these cathode rays, and let me flash forward a little bit here. Here's an example of a cathode ray tube. So you have a cathode where you have these negatively charged particles, and they're traveling across this vacuum. So he says, this current here, this ray, is made from some kind of particle. And if you put a magnet up to it, it will move towards one end of the magnet and away from the other end. So it'll move towards the positive end, away from the negative end. So he's like, these cathode rays are made up of some kind of negative particle. And this negative particle must be coming from an atom. So he comes up with the idea that the atom has these negative particles in it. And he calls this the plum pudding model of the atom. Now, you can't think of pudding like we generally think of pudding here in America right now. You'd probably thinking like Jell-O pudding or something, but that's not their type of pudding. If you ever watch like the Great British Baking Show, they have a little bit different idea of pudding. Back in the day, like a Christmas pudding would have been more like a gooey fruit cakey kind of thing with chunks of, in this case, plums in it, floating around in it. So he said that those chunks were like the negative electrons, And that pudding, that dough, was just this overall positive charge that went with it. So, a better analogy for us today might be the chocolate chip cookie model, where the electrons are just these chocolate chip cookies, these negatively charged particles that are just floating around willy nilly in this positive cookie dough. So, if you want to think of it as the chocolate chip cookie model, you can if it helps you. So, again, where did he get this idea? He knew that this gas was inert and it was neutral, and that if you applied electricity, these negative charges would come out and cross this vacuum. So he's like, okay, these negative charges have to be coming from these neutral atoms. So there must be a negative piece inside the atom. He also thought, well, if there's a negative piece, there must be a positive piece, but he was never able to isolate that. So, Thomson, what you need to know. He concluded that the negative charges came from within the atom. So, this breaks apart Dalton's atomic theory. Now, there is something smaller than an atom. The atom is divisible, right? So, that is a huge blow to Dalton's theory. There is now something smaller. He called these things corpuscles. Today we call them electrons. If we ever get back in school, I'll show you. I have an old textbook from turn of the century, 1900s, and it has no mention of electrons or neutrons or any of that stuff, but it does mention corpuscles. Since the gas was known to be neutral, having no charge, he said there must be some positive piece too, but he was never able to isolate the positive piece like he was the negative piece. So once he discovers these negative electrons, another scientist, Millikan, comes along, and he's trying to find out more about these electrons. So long story short, we won't go too into his experiment, but he winds up using this oil drop experiment to determine the size and the charge of electrons. Basically where that one went, excuse me. Then there's radioactivity. So also around this time, people are discovering radioactivity. So Becquerel, I believe is maybe how you say that name. Becquerel he was working with uranium, and he found out that it exhibited radioactivity. So it is emitting some form of radiation. So we're going to get much more into radioactivity later, but we'll talk about alpha, beta, and gamma radiation that can come from these particles. You've probably heard of Marie Curie and her husband Pierre that isolated two other elements, radium and polonium. They did a lot of work with that. And of course, Marie Curie wound up dying because of her work that eventually gave her leukemia. To this day, her notebooks are sealed away. They are too radioactive to even handle. But they didn't, of course, know that that was happening to them. Like I said, science takes time. So they're working with these things. They find them really interesting, and they have all these amazing properties, but they didn't realize that one of the side effects was the damage they were doing to their bodies. So in studying these, discovered radiation is given off chemically, and you have chemically changed the properties of the sample. So when some uranium gives off these radioactive particles, it's no longer uranium anymore. It actually changes from one thing to another. So that's pretty big idea that an atom can change. All right. So the next person to come along who's also working with these radioactive samples. So we said one of the particles was alpha particle. So Ernst Rutherford has this alpha particle gun, and he designs this experiment that winds up really shedding some more light on the atomic structure, even though it wasn't what he intended to necessarily do. So his experiment was he had this gold foil, and like gold foil is like really, really thin pieces of gold. So it's only about 2,000 atoms thick. And you might think, oh, 2,000 is a lot, but not when you're talking about atoms. So very, very thin pieces of gold. And starts shooting alpha particles at this gold foil. Oh my gosh. Just a second. So he starts shooting these alpha particles at this gold foil. And of course, he's operating under the assumption that Thomson is correct. So what he expects to happen is that well, let me flip forward here. Well, go back to we'll just go this way. So he expects most things to just fly right through because in Thomson's model, there would have been like no positive pieces, just this background positive goo, right? Dough. So what happens though is he shoots these alpha particles into this gold foil. He expects they should shoot right through, maybe veer off a little here or there. But what happens is not only do they veer off in these really, crazy angles, some of them even come back and get detected coming back at him. And if Thomson was right, this should never happen. So Rutherford describes it as as if you took a gun and you shot a bullet at a piece of tissue paper and it bounced back and hit you. That just should not happen. So in order for these positively charged alpha particles to bounce back, they have to be hitting some dense positive piece. So they have to be encountering some positive piece to it. So here's his experiment sort of design. You have your alpha particle gun shooting at this gold foil, lots of detectors around. He expected most of them to go straight through, maybe veer off a little bit, but they did more than that. They veered off at these angles and even came back this way. And if this is going to happen, there has to be some positive piece in there to repel it and send it backwards. So Rutherford now has discovered that there is a densely charged positive piece to it. So the difference would be these. This is Thomson's model, where you have these negative electrons and this sort of background positive goo. Things should have shot straight through it. But in Rutherford's model, you have, there's a densely positive piece, and it's coming back to make these alpha particles come back at you. So this means, according to Rutherford, that the atom is mostly empty space. It's not this pudding thing, right? It's mostly empty space that's allowing most of the alpha particles to fly right through. But when they get sent back at them, there must be some small, dense, positively charged center that's repelling them. And he calls that the nucleus. So he's thinking like biology, a cell has a nucleus in it. So he calls that the nucleus. He says it's very tiny compared to the atom as a whole. So now you have Rutherford's model of the atom, where you have electrons surrounding this densely positive central piece, but this is mostly empty space around it. So you now have a nucleus and electrons around it, but there's not really any structure to the electrons yet, so it's just kind of willy-nilly. Your book kind of stops here for now, but I'm just going to tell you where things are going. Next, we're going to talk about a guy named Bohr, who comes up with specific energy levels. So he says those electrons aren't just willy-nilly. They orbit around the nucleus. So you can think sort of like a planetary model. There's energy levels that are assigned to these orbits, and electrons can jump from one to the other. Now, we know now that this only works for one atom, Bohr's model, but it is a really simple way to describe the atom. So we still use Bohr's model in, all up through high school. But the actual current modern model is the wave model. And this has electrons traveling in these wave-like patterns. We'll discuss this more later on, but just to give you an idea of where things are headed. So today's atomic model is based on wave mechanics. And according to the wave mechanics, electrons don't move on these defined paths. So it's not like planets going around the sun. They actually travel like waves. And you just are going to be able to figure out not exactly where they are. You can't know exactly where an electron is and where it's going, But you can give probabilities and say this is where the area where it should be. So again, more to come on this later. We're just hitting on the high notes right now. But we still got that small nucleus in the middle and this electron cloud. So that is getting us to that atomic model that you've probably seen before. So more on that later. So let's kind of look at everybody here. We have ancient Greece. They just said it's an indivisible thing. Dalton, pretty much saying the same thing. Thomson comes along, adds an electron to it. Rutherford says, I see your electron, and now I've found a nucleus. And Bohr says, got your electrons in your nucleus, but I'm going to add some order to the whole thing and add orbits into it. And although that's a great, nice, it makes sense to look at it this way, it's actually more complicated than that, like most things in life. So the new model has this wave properties in the electron cloud. So more to come on that later. For now, though, you should be ready to go to answer the questions in that Google form for 3-2. Have a good day.